Check it out now, y'all.
NanoHub U, online instruction.
So in this lecture, I'd like to do some sample problems, sample examples to illustrate this partition function that we discussed in the last lecture. And in the three examples I'd like to talk about are hydrogen atoms at 1000 degrees Kelvin. I'd like to talk about a two-state spin system and an external magnetic field. And then I'd like to discuss a simple model that has three energy levels, but in this model, the density of states for each energy level is going to increase rapidly with with energy. So this illustrates some of the features of this partition function that's very useful. In addition, I put into the appendix a quantum gas model. This is a three-dimensional calculation that basically describes the Maxwell-Boltzmann distribution function. If you recall, a few weeks back, I wrote that distribution function down, but I did not derive it. If you want to know where it comes from, right, this is a derivation. It's got all the details, so you can take a look at that. So let's begin with the hydrogen atom at 1000 Kelvin. So the premise here is we've got a collection of hydrogen atoms. They're in thermal equilibrium at 1000 Kelvin. And the question is simply how many atoms are in the n equals 2 quantum state. So to do that calculation, we have to know something about the quantum system. And I just write down what we already know. In this calculation, I'm just going to worry about the three lowest energy states. So this is the n equals 1, the n equals 2, and the n equals 3 energy levels. I translate those energy levels with respect to this zero reference in energy. I just translate those energies over to this part of the diagram, where now I label the lowest energy state at 0 electron volts. The first excited state is going to be at 10.2 electron volts. The third state is going to be at 12.1 electron volts. And then in addition, I list the degeneracy of each energy level. That degeneracy is equal to 2n squared. So this calculation, I'm explicitly including the spins in the calculation. So as you probably gathered from the previous lecture, all these calculations start with an evaluation of this function called the partition function. It's just the product of the degeneracy times the Boltzmann factor for each energy state, and you have to sum over all states. So for this calculation, I'm just including three energy states. The reason is pretty simple, because when you evaluate the second and the third term in this series, you'll find that the contributions to Z are very, very small. They're insignificant. So the value for the partition function for this case is 2. Now the reason these second and third terms in this sum for Z are small is because the value for KT even at 1000 Kelvin is about 0.086 electron volts. That should be compared to energy levels that are occurring at 10 and 12 electron volts above the ground state. So this ratio of the argument of the exponent is a large negative number, and it just basically means that the contribution from the second and third terms to the partition function are negligible. Once I know the partition function, then I can calculate the probability that there's an atom in the n equals 2 quantum state. That's just given by the number of ways that second quantum state can be realized. That's G of E2. In this case, that's equal to 8. And then I have to include the Boltzmann factor which in this case involves the energy difference between the ground state and the first excited state. That's 10.2 eV. KT, I've already mentioned, is about 0.086 electron volts. And so when you evaluate that probability, what you find is you find an incredibly small number, essentially 0, and that's just telling you that even at 1,000 Kelvin, the probability that a hydrogen gas atom is in this first excited state is essentially 0. So just by thermal excitation alone, the chances that you get a hydrogen atom, or the chances that you get an electron excited from the ground state to the first excited state in a collection of hydrogen atoms, that probability is essentially 0. So that's what this calculation is trying to tell you. And the important thing to remember from this calculation, not so much as the final result, but the way the formalism for this partition function is applied to sort out the answer to the question. The second example I'd like to run through is the two-state spin system in a magnetic field, and I'd like to explicitly include the temperature in this discussion. This is a standard problem. You find it in every textbook, so it's probably worthwhile to understand it in some detail. What you need to know is information that we've already covered in the course. You need to know that the spin of an electron is 1/2, so that the magnitude of the spin of an electron is the square root of 3/4 times h bar. You need to know that the projection of the electron spin along a z-axis, and the z-axis in this case is going to be determined by the direction of the applied magnetic field. You need to know that that spin has plus minus 1/2 eigenvalues when you project its magnitude onto the z-axis of the coordinate system. The problem is not so much concerned about spins, but it's more concerned about magnetic moments. So we've got to convert spins into magnetic moments. And just by way of review, I'll just mention that an electron orbiting a hydrogen atom has an orbital contribution to the magnetic moment, and I work out what that orbital contribution to the magnetic moment is. It depends on this quantum number m sub L, which in this case we're going to set equal to 0. So we're going to neglect the orbital magnetic moment. Instead, we're going to focus on the magnetic moment that's produced by the intrinsic spin of the electron. The intrinsic spin of the electron contributes to a magnetic moment by the z component of that spin. There's a g factor that's associated with this calculation. That g factor is essentially equal to 2.0. And when you work through the arithmetic, right, what you find out is you find that the magnetic moment contributing to the, you find out that the spin of the electron contributes a magnetic moment that's just equal to the Bohr magneton for the electron. So there's a minus sign that has to be properly taken into account to this discussion. So the magnetic moment is always opposite to the direction of the spin of the electron. That's basically what the minus sign is saying. And for our purposes, we're interested in the potential energy that this spin will have in an external magnetic field. And this is the quantity that we're going to evaluate on the next slide. So what's the relative energy of a spin up and a spin down state? Well, when there's a 0 applied magnetic field, the spin up and the spin down electron are degenerate. They have the same energy level, and we'll call that energy level, just for sake of argument, equal to E0. Now, what happens is the magnetic field increases, right? The potential energy of the spin down electron decreases. The potential energy of the spin up electron increases. And that change in potential energy is just related to the formula here, which expresses the potential energy of a magnetic moment in an external magnetic field. So these red arrows here are not magnetic moments, they're actually spins, and so I'm going to be talking about spin up and spin down electrons, right? The lowest energy state for a spin down electron in an external magnetic field is when the magnetic moment of this spin down electron aligns with the magnetic field. And what basically happens is the energy of this spin down state decreases from this value E0 by a quantity that's just equal to the magnetic moment of the electron times the applied magnetic field. In contrast, the energy of the spin up electron increases by the same amount from its value, from its energy eigenvalue when the applied magnetic field is equal to 0. So these are the two states that develop as the magnetic field increases. It's very convenient to relabel those two states, designating the lowest energy state as equal to 0. The upper energy state is going to be separated by this quantity 2 mu times B0. The real issue in this calculation is what is the size of the thermal energy? What is KT? And in particular, what is KT with respect to this energy splitting? So you might expect that if KT is very large compared to this energy splitting, then the probability that the electron has a spin down or a spin up state is 1/2. So there's no net probability that one of these states is going to be occupied more than the other. Conversely, if KT is a small number compared to this energy splitting here, so if KT is a small value, then it becomes energetically favorable for the electron spin to be in this energy state rather than this one. And that just simply means there's going to be a higher probability that the electron has a spin down value than it has a spin up. And that's going to lead to a net magnetization, a net magnetic moment for this electron. So that's the thing that this partition function now has to calculate. It has to evaluate KT with respect to the applied magnetic field. The calculation that's appropriate for this system, I sketch out on this slide. And I just remind you that the probability that an electron is going to be either in the spin or up or the spin down state is going to be related to the degeneracy of that state times the Boltzmann factor divided by the partition function. And in this case, we're going to assume that the degeneracy of each state is equal to unity. So for the spin up energy level, the spin down energy level, both energy levels we're going to assume has a unit degeneracy. And so that just means that it's pretty simple to calculate the probability that we have a spin up electron. And what we need to do is we need to use the energy of that spin up electron. And in this case, it was just equal to 2 mu B. That has to be divided by K Boltzmann T, right? We also have to evaluate the partition function, which is just the sum of in this case, it's the sum of the Boltzmann factors for the two states. It reduces to this value simply because the degeneracy is equal to unity. So this is then the probability that we find an electron in the spin up state. This is then the probability that we find an electron in the spin down state. The spin down state, you recall, we defined the energy to be equal to 0. So this numerator is by definition equal to unity. The net magnetization of the system is then going to be the magnetization for each state, mu sub I, times the probability that that state, P sub E of I, is occupied. And we just worked that out in this line, and we can make an algebraic substitution here, and we can rewrite the exponential terms in terms of a hyperbolic arc tangent. And that hyperbolic arctangent now expresses basically the net spin that the electron is going to have, or the net magnetic moment that electron is going to have, as a function of the applied magnetic field B naught and as a function of the temperature T. So the argument of the hyperbolic tangent is this quantity mu B naught over K Boltzmann T. The quantity that multiplies the hyperbolic tangent is just the Bohr magneton. So then this is the expression for the magnetization of an electron in an applied magnetic field as a function of B naught, the applied field strength, and as a function of the temperature T. So in the next slide, I just plot this function just to show you how it behaves. So this would be the net magnetization of this electron in an applied magnetic field. So I plot magnetic field along this axis, and I do the calculation for 3 different temperatures, 1 Kelvin, 5 Kelvin, and 10 Kelvin. And what you can see is that for very low temperatures, temperatures of about 1 Kelvin, you can see that the magnetization increases linearly from 0 up until about 2 Tesla. When you get to an applied magnetic field of 2 Tesla, the splitting between the spin up and the spin down state becomes large compared to KT, where T is 1 Kelvin, and so the magnetization then saturates as the magnetic field increases. That situation should be contrasted to the case when, let's say, the temperature is on the order of 10 Kelvin. When the temperature is on the order of 10 Kelvin, you're going to need very large magnetic fields greater than 10 Tesla, to split the energy states by a sufficient amount such that the thermal energy is small compared to the separation between the 2 energy states. And so as a result, the magnetization has a behavior as a function of magnetic field that's indicated by the green line. So this is a standard result. It's found in all the textbooks, and I wanted to go through it and just show you how that result is derived. And hopefully you'll be able to understand it. You'll be able to see the advantages of this partition function formulation of the problem, because once you evaluate that partition function, these results drop out really very quickly. It's a very nice and simple derivation. The third example I wanted to discuss is a situation that I kind of cooked up artificially, and I wanted to use it to discuss the effect of this degeneracy of each quantum state. So let's review the system very quickly. The system has 3 energy levels. I call it E0. This is the ground state. Then there's an energy level E2 and an energy level E3. And I say that that the energy level E2 is about 4 kT above the ground state level. I say that the third energy level is about 9 kT above the ground state level. And for this initial calculation, I'm going to just assume that the degeneracy of each state is the same. It's a quantity called A. I don't really care what A is, but that's what the degeneracy is. And what I want to do is I want to answer 2 questions. First question I want to answer is, what's the probability that I would find a particle in this energy level E2? And the second question I want to answer is, if I measure thousands of particles that have been distributed into this system, right, what's the average energy of the particle that I'm going to measure? So I have thousands of these systems. I drop 1 particle in each system. I let it equilibrate, and then I come and I measure somehow the average energy of the particle in each system. I make 1,000 measurements. What's the average energy of the particle that I'm going to get when I average all those 1,000 measurements of energy? So let's do the first problem first. What's the probability that this energy state E2 is filled? So by now you should get the picture that all these calculations start by evaluating this partition function Z. And in this case, the partition function Z is easy to evaluate analytically because it contains, there's only 3 energy states, and the separation between the energy states are cooked up to be integer multiples of KT. So that just means that when you evaluate the Boltzmann factor in the partition function, right, you end up with very simple expressions for the Boltzmann factor. And you can evaluate those, and you find that the partition function is about equal to unity, right? So that's already telling you that most of the particles are going to be in the ground state energy, right? Because this quantity is on very close to 1, right? Probability that the particles in energy level E3 is 1.2 times 10 to the minus 4. You can see this degeneracy factor A cancels out because it appears both in Z, and it also appears when I have to insert a value for G of E, right? So 1.2 times 10 to the minus 4, that's about 1 in 8,250. So that would mean that I would have to sample this system roughly 8,250 times before I would actually find one particle that's in this energy level E3. It's very low probability, and that's just a reflection of the fact that the thermal energy that the particles have is small compared to this 9 kT separation in energy. The other question I can ask is, what's the average energy of a particle in this system? Well, the average energy is going to be expressed by the energy of each state times the probability that a particle is in that state. And the probability that the particle is in that state, I've already worked that out here, so you just have to include that in the sum, and you have to subscript the energies now with the appropriate subscripts for each energy level. So I can now evaluate this sum explicitly. I worked that out in about 2 or 3 lines. And at the end of the day, again, you're going to see that this degeneracy factor A cancels out because it appears both in numerator and denominator. And at the end of the day, you find that the average energy of a particle is about 0.07 kT, which just basically means that most of the particles are residing in this lowest energy state. Okay, so that's the simple case where the degeneracy for each system is the same. Now, it turns out in a lot of these quantum systems, right, the density of states, the number of ways you can arrange particle in a different energy level, that density of states G increases usually as some power of energy E, and this power alpha is a quantity that typically is greater than 1. So for this example, for part 2 of this example, I just like to assume that the density of states increases quadratically with energy, and I like to try to find out what the consequences of that simple assumption are. Again, this is a common feature of all these quantum systems. The higher up in energy you go, it turns out the more states are available for the particle. What I'm trying to convince you of is that this very simple realization has some rather dramatic consequences when you calculate probability that a particle is in the energy level E3 and when you calculate the average energy of a particle in the system. So the degeneracies now for our 3 states, assuming this quadratic dependence on density of states with energy, our degeneracies are now A, so the ground state energy is the same. The second energy state is going to have a degeneracy of 16A, and the third energy level is now going to have a degeneracy of 81A. So that's going to have a big consequence, right, when you evaluate the partition function. And so I work through that calculation here. I have to use these new degeneracy factors when I evaluate the partition function. What I find out now is that this partition function is about 1.3 times this quantity A. And that just simply means that if I calculate the probability that I find a particle in the third energy level, in energy level E3, right, I have to take into account the fact that the energy level E3 is now degenerate by this quantity 81, so that has to be included explicitly in the calculation. Again, this factor A cancels out, and what I find out is I find out that the probability that I find a particle in energy level E3 is now about 7.7 times 10 to the minus 3, which is about 1 in 130. So that means that instead of sampling the system 8,250 times to find one particle in energy level E3, now I could sample the system something like, well, 130 times, and I would then find a particle in energy level E3. So there's about a 64-fold increase in the probability that the highest energy level state in this system is occupied. And that 64-fold increase just comes about because we've assumed that these density of states is increasing rapidly with energy. Again, to finish the discussion, I have to ask, what is the average energy of the particle in this three-level system? And the calculation proceeds in a way very similar to what we've already shown, except now I have to take into account the fact that the degeneracies of each energy level are different than they were when I originally did this calculation. Again, the quantity A cancels because it appears both in the partition function Z, and it also appears in the numerator when I evaluate these explicitly evaluate this G of E for each energy level. And at the end of the day, when you run through the numbers, what you find out is now the energy level E is on the order of KT rather than 0.07 KT. So just by increasing the degeneracy of these higher energy levels, you can change the average energy of the particle in the system by quite a bit, right? And that's what this calculation is trying to show. So the diagram in the yellow box here illustrates the two situations. First situation, I just assume that the degeneracy is the same for each energy level. The second situation, I assume that the degeneracy of each energy level increases. In this case, I just made the simple assumption it increases quadratically with energy. And we just investigated the consequences of this fact, which turns out not to be too far from what actually happens when you look at quantum systems where the number of energy levels is very, very high. So this is a characteristic feature of quantum systems. The density of states always tends to increase, at least in 3 dimensions. The density of states always tends to increase as the energy goes up. So that's the take-home message. So I'm running a little late. I gotta stop. Up next, we want to answer the question a bit more quantitatively when we use quantum statistics. We've been dancing around this question during 2 or 3 lectures in this course. We're now going to try to lay out some quantitative guidelines that help you decide when you use classical, when you need quantum statistics. And we're going to do that by defining something called a thermal de Broglie wavelength. So when you get a chance, come on back and listen to that lecture. It's kind of interesting because it solves a problem that we've discussed back and forth many times throughout the semester.